Right, so welcome everybody. So today we have Luis Izquierdo, many of you know well, talking to us about successful strategies in the voluntarily repeated prisoner's dilemma. So over to you, Luis.
Okay, thank you very much, Jonathan. Thanks a lot for organizing these seminars and for inviting me to present this work that I've had the pleasure to do with my brother Sergis Izquierdo and with Rob Boyd, who actually was the originator of this idea and is currently at Arizona State University. Before I start, I don't think I have to say it, but there's many of you know a lot, probably more than me about this topic. So please do feel free to ask any questions, make any comments, ask for clarifications, or do whatever you like. I think we're all gonna get much more out of this seminar if we see it as a seminar rather than just a regular presentation. So feel free to jump in whenever you like, please. I'll appreciate that. Okay, so let me see. Okay, so we all know how important cooperation is, not only to human societies, but also in biological systems in general. And in this seminar, what we're going to do is to study one mechanism that can lead to the evolutionary emergence of cooperation. And we're going to use, as most papers in game theory that study cooperation, we're going to use the repeated prisoner's dilemma, but we're going to do something different. Most papers, if not all papers that deal with the repeated prisoner's dilemma, make at least one of the following three assumptions that we have here. Most papers assume that there are no errors or mistakes, or that these errors occur with extremely low probability. They study the trembling hands noise, if you like, or the limit when the error rate goes to zero. Some other papers include mutation, but it's often the case that they study the behavior of the system when the limit of mutation goes to zero. And most papers in the literature do not consider the option to leave, though we all know here that in the last 10, since Takako's paper, well, even before, but since Takako's paper, I think there's been a growing literature that studies the option to leave. And what we're going to do in this paper is to make, to study a setting, an environment where there are significant errors, there is a significant amount of mutation or experimentation, if you like. So there's a constant influx of new strategies coming into the system. And what we want to do is to study in this setting with persistent variation and common errors, does the option to leave lead to greater cooperation or to less cooperation, or does it make any difference? That's what we want to study here. Before I proceed, so for the purpose of this presentation, I'm going to use mistakes and errors interchangeably. For me, that they're going to be the same thing. And by that, I mean if a player makes an error when they choose the unintended action in the prisoner's dilemma. So if their strategy dictates to cooperate at a certain point, they will defect, and the other way around. And this will happen with probability epsilon. And then we're also going to include mutation or experimentation. I'm going to use those terms interchangeably. And by that, I mean that there will be a constant influx of new strategies, random strategies. So in biological systems, you can see that reproduction leads to our offspring with a random strategy. And in economic systems, where you usually assume that players do not die and reproduce, but revise their strategy, I'm going to assume that they experiment. From time to time, they test a random strategy, and they do so with probability mu. Any questions or comments about what we're going to do? Because this is pretty much the basic setting. No? Okay. So why are we interested in settings with significant amount of errors and mutation or experimentation? Well, first of all, because of its empirical relevance, right? It's most real-world systems of interest, I think, are characterized by some persistent variation and the possibility that agents make errors. A second point is the distinction between small error rates or small mutation rates and vanishingly small mutation rates or error rates. So here we're going to study error and mutation rates of the order of 1, 2, 3, 4, 5%, something like that. And what many scholars have already noticed and published is that very often evolutionary dynamics behave very differently when you study them when the error rate is 0 or close to 0, or you take the limit of the error rate towards 0. It behaves very different from when you assume that errors can be more significant, that they can be 1%, something like that. And this is what I wanted to illustrate with this figure that we will discuss in detail in a few minutes. But basically in this figure, what you see is the distribution of the unique attractor of a system, okay? So it's a system with 5 strategies with different colors, OD, Tit-for-Tat, Win-Stalus shift, Grim, and Lever 1. Doesn't really matter the meaning now, but this is the distribution of the unique global attractor as a function of the error rate. And what we see is that when the error rate is 0, when there are no errors, or when these errors are very small, the unique global attractor basically is composed mainly of 4 strategies and a little bit of OD. And then for error rates just above 2 times 10 to the minus 3, you get a completely different global attractor. And this is something that is observed reasonably often in evolutionary systems in our experience. And then the last reason we're interested in significant amounts of errors and experimentation is more technical, more mathematical, but also, I mean, I thought I should mention it, is that very often when you include significant amounts of error and mutation, predictions become sharper. We're all aware of the fact that in repeated games, very often when there are no errors or mutation, you can find infinitely many equilibria, like Nash equilibria in the repeated prisoner's dilemma, or none. Sometimes depending on the type of equilibrium you're interested in. So if you're interested in evolutionary stable strategies, you find that in the repeated prisoner's dilemma, there are none. So this problem of indeterminacy, if you like, is often disappears when you add a substantial amount of mutation and experimentation rate. It makes sense, right? Because I mean, if you take a mutation or experimentation to the maximum, you know there is one single global attractor. So at some point, there will be one. What is interesting and what we're going to see here is that there is a wide range of values for the mutation or the experimentation parameter at which you still preserve the strategic nature of the game, but you only have one or very few attractors. Okay, so these are the main reasons we're interested in this setting. So, and what we're interested to see is how does the option to leave, how does having that option to leave your partner affect cooperation rates and affect the success of different strategies? If you try to answer this question using a traditional equilibrium analysis, some of the information that you may find useful is what we see in this table. Okay, so if we focus on the first column is for the repeated prisoner's dilemma, so no option to leave. And if there are no errors, the Folk theorem tells us that there is infinitely many Nash equilibria, And many of these, infinitely many of these Nash equilibrium support full cooperation if the continuation probability is sufficiently large. There are no evolutionary stable strategies, since any Nash equilibrium can be mimicked of the equilibrium path, but the Nash equilibrium, there are infinitely many that support cooperation. If you add errors, small errors, like vanishingly small errors, then the picture changes a little bit, because you can find evolutionary stable strategies, and you can even find strict Nash equilibrium that support full cooperation. So in terms of equilibria, what we see is that in the repeated prisoner's dilemma, there are infinitely many equilibria of one sort or another that can support full cooperation. And this is completely different when you add the option to leave. If you add the option to leave, there are certainly Nash equilibria that support partial cooperation, as Takako identified now almost more than 15 years ago with the trust-building equilibria. And even though these equilibria support partial cooperation, there is no Nash equilibrium that supports full cooperation, right? Because we always have this strategy that can defect and leave. So any system where everyone is cooperating is easily invadable by this defect and leave strategy that just defects and goes to the next partnership. And then there is no...
Excuse me, Luis. May I just ask you a clarifying question?
Sure. Yeah, thank you. Yeah, tell me.
Oh,
Jorgen. Hi, thank you. How are you?
Fine, and you?
Fine.
Are you?
Yeah.
Very good. No, this is an interesting topic. I just wanted to, could you clarify when you see the option to leave? That will depend very much on what it is that you have if you leave. I mean, what is the alternative option?
What you mean? You want me to clarify the option?
Clarify what do you mean by leave? If you leave a partnership, do you rematch with a random guy, or what? Can you tell what is the story?
Yes, sorry. I will explain this in detail in 3 slides, but it's basically what you said. You leave and then you go to a pool of singles where there's other people who left or were left by their partners, and there's random matching within that pool of singles. Is that clear enough for now? Or yeah, thanks. Thanks a lot, Jorgen. Thank you so much for asking. Okay, and please, yeah, if anyone finds that something is not clear, or wants me to clarify something, please, I very much welcome questions during the presentation. Okay, so given this equilibrium analysis that we were discussing, one maybe could infer that cooperation is going to be easier in the repeated prisoner's dilemma compared with the voluntarily repeated prisoner's dilemma, because in the repeated prisoner's dilemma, there are many Nash equilibria that support full cooperation, even strict Nash if there are small errors. But in the voluntarily repeated prisoner's dilemma, no Nash equilibrium can support full cooperation. But what we're going to see in this setting, and what, for instance, Grasser, Matthijs, Takako, Julian showed for a setting with no noise, is that that it's the other way around, actually, that for sufficiently large probability of continuation, cooperation is greater and more robust when you have the option to leave, okay? And we're going to see this. We're going to see also that when you add substantial amounts of error and experimentation, you often observe just a very reduced set of winning strategy, a very reduced set of dynamical regimes towards which the model converges. And in this particular case, this dynamical regime in the voluntarily repeated prisoner's dilemma is sustained, is supported by strategies that leave defectors, basically. And all the strategies that do not leave, the strategies that appear in the repeated prisoner's dilemma, basically vanish in these systems. So this is pretty much what we're going to see. Now I'm going to present the model, and hopefully Jorgen's question will be clear. But if you have any questions so far, please do jump in. Okay, so we only have 2 slides for the model. So I'm going to take some time to explain them well. And after this, if someone has any questions, please ask them. Okay, the first thing I want to make clear is that what we're going to do in this paper is to study a system with a reduced strategy space. Okay, we're going to look at memory 1 strategies. These are strategies that can condition their action on the last outcome of the interaction. So if you look at the first row of this table, the dark green, you see the possible outcomes, last outcomes that you may observe. You've got the empty outcome, if you like, which is what you observe, if you like, when you meet a partner for the first time. And when you meet a partner for the first time, you may choose to cooperate or defect. And then once you've played at least once with your partner, you will observe that the last outcome in that partnership is either a CC, CD, DC, or DD, any of these 4. The first letter is what you did. The second letter is what your partner did. And for each of these 4 possible outcomes, you may choose to stay and cooperate the next round, to stay and defect the next round, or to leave. And when you leave, you're going to go to this pool of singles that have left their partner or have been left by their partner, and you're going to pair up with another one at random. So what is our strategy space? So in the voluntarily repeated prisoner's dilemma, we would have 2 times 3 times 3 times 3 times 3 strategies, which is 164 memory 1 strategies. They're all pure strategies. We're only considering pure strategies. And the way we study the repeated prisoner's dilemma is by using only the strategies that never leave. And these are 2 to the 5th, right? 2 to the 5th. And those are 32 memory 1 strategies that do not leave. Just to give you some examples, so Tit-for-Tat is the one you can see here, CD, CD. So it starts cooperating. Then if the previous outcome is CC, it cooperates. If the previous outcome is CD, so the other player defected, it defects. If the previous outcome is DC, so Tit-for-Tat defected probably by mistake, it will still cooperate. And if the previous outcome was DD, it will defect. Okay, so this the strategy space we're going to consider. And this slide is probably the most important one. This summarizes the whole model. So I'm gonna go slowly through it, and please do ask anything that is not clear. Okay, so initially, we're looking at the left in the figure. Initially, there is a population of n players, and initially, at the very first period, they're all single. Okay, they're all single, and they're randomly matched to play the prisoner's dilemma. Actually, what we're gonna study is a version of the prisoner's dilemma called the donation game, where we only have 1 parameter. So players you can think that they have 1 unit, and they may give it to their partner. And when they do so, they lose that unit, but the partner receives B, where B is greater than 1. So B is the benefit for a unit that has a cost of 1. That is the game we're gonna consider. So it's parameterized just by this single parameter B for benefit. And in this, when they play the prisoner's dilemma here, they may choose an unintended action, they may make a mistake, they may make an error with probability epsilon. Okay, and this is going to be substantial. In the baseline scenario, it's going to be 5%. And then after they have played, then they may suffer some exogenous breakup. So with some probability, any partnership will break. Okay, so the way we model this is with a continuation probability. So there's a continuation probability delta that a partnership will survive. And with probability 1 minus delta, the partnership will break, and then both players will become single. And partnerships may also break because they have a strategy that detects that they should leave. Okay, and that we're gonna refer to that as endogenous separation. And once they've played the game and there's been potentially an endogenous separation and potentially an exogenous separation, the players who have been exogenously separated, they may revise their strategy with a certain probability R. And if they do so, when a player revises their strategy, they do it as follows. With probability mu, they experiment, they choose a random neighboring strategy, and with probability 1 minus nu, they imitate another player with probability proportional to player's payoff. Okay, so the mean dynamic of this will be, or if this was a system without the option to leave, it will lead to the Maynard-Smith replicator dynamics. Okay.
Can I ask a question?
Sure, thanks. Yeah.
So neighboring strategy, is that in a mutation space or is it in a physical space?
Neighboring strategy, it's not very important, but the way we implemented mutation is that if you mutate or if you experiment, what you do first, imagine you have a certain strategy that is determined by 5 letters, 5 genes, if you like, or 5 letters. You're going to choose one of those letters at random, one of those positions at random. And once you've chosen one of those positions at random, you're going to choose one of the options with equal probability. That's why I said neighboring.
Yeah.
Results are not affected by that. So I think you can safely assume that it's random also. But the results I'm going to present, even though I think they will be the same, but the results are with this mechanism. Is that clear?
Yes, very good. Yeah.
Thanks. Yeah. It's something that, Rob is much more concerned, fortunately, about empirical relevance, and he thought that it made much more sense to implement mutation like that. But I really think, and it's not only that I think, we've checked that this is not, it doesn't make much of a difference at all. Actually, what we did was to implement this in an agent-based model that it's freely available if anyone wants to play with it and check our results. And the problem when you study systems with high mutation rate, with high error rate, is you gotta choose numbers. Okay, you're gonna choose numbers. You're not taking limits. You're gonna choose numbers. So we started with what we call the baseline scenario that I'm gonna describe now. But what we're gonna see in the next slide is that everything we're gonna see today is pretty robust. You can change each of these parameters independently, and within a wide range, you're gonna observe the same kind of behavior. Okay, so what are the parameters? All the parameters of the model? Yes.
One second. There was a couple of questions from the audience,
Sure.
I think. So I see Philip Neri has one.
Yeah.
I just had a clarification question about
Sure.
the voluntary repeated prisoner's lemma. So what does the action L actually mean? If I choose L, what happens in that period?
Actually, I'm super glad you asked that, because I didn't explain it very well, that even though it's okay, sorry, thanks a lot. So if you choose L, okay, imagine you and me are playing, and we play, you choose cooperate, I choose defect, and you say, okay, after CD, I leave. My strategy says that I leave. So what happens is that you and me, since we have broken our partnership, we're gonna go to this pool of singles. We're singles. There will be other players who do not choose to break, and there will be the remaining pairs here. And then in the following tick, in the following discrete time step, all the singles, so you, me, and everyone who has their partnership broken, will be in this pool of single and will be randomly matched in pairs to repeat the whole process.
But it's really every time that I'm matched, we do play the game, and then I also have the option to leave afterwards.
Exactly. And we play one stage game. Okay, what we're saying in this slide, you play one stage game. You play the prisoner's dilemma once, and then everyone will decide whether to stay or leave. And if both players decide to stay and they're not exogenously separated, they will stay as a couple for the beginning of the following period. But if one of them decides to break, or if they're exogenously separated, they will join the pool of singles, and everyone in the pool of singles at the beginning of the period will be rematched at random. Please do ask anything that is not clear. Is it clear? Or?
I think it's clear.
Yes. Yeah.
Okay, thank you. Thank you very much. Thanks very much for asking that, because I don't know why. I should have explained that much more carefully. So thanks a lot. Okay, so if there's any more questions about the model, please do ask, because now there's no more model, if you like. The only thing we're gonna see is some results and try to understand the results. So if you have more questions, please, now it's the best time to ask. Anyway.
Oh, I have one more question.
Great, thank you.
If you don't leave, you don't revise?
No, that's a very good question. Okay, this is tricky, okay? Because we don't want the revision we want every player, regardless of their strategy, to be equally likely to revise their strategy, okay? So for instance, one thing that we considered, but it is not satisfactory, is, okay, whenever you go to the pool of singles, you revise your strategy with a certain probability. That is not good, because some strategies will break more often than others, and those strategies will go to the pool of singles more often. And if we had done it like that, then these strategies will revise their strategy more often than others. And what we wanted is a process where every player, regardless of their strategy, would revise with equal probability. To do that, what we do is the only ones who have an opportunity to revise their strategy with probability R are the singles who have been exogenously separated. Okay, so only when you're exogenously separated, and every player, regardless of their strategy, is equally likely to be exogenously separated, only when that happens, you have the opportunity to revise your strategy. So in that way, there's no bias. Is that clear? That's a very good question.
Yes, it's clear to me. Thank you.
Thanks. Thank you very much. Great. Thank you so much, guys, for asking these questions. Okay, so we're going to look at this baseline scenario. The baseline is a payoff benefit of 3. In my opinion, nothing outrageous. So expected number of interactions of stable couples 20. So if there's two strategies that will not decide to break endogenously, their partnership is expected to last for 20 periods, okay? It's a geometric distribution. There's always a probability in each step that it will break, but the expected number of interactions of stable couples is 20 periods. Then there's a 5% probability of error, a 5% probability of experimentation or mutation. There's a 10% probability of revising whenever your partnership has been exogenously broken. And we consider populations of 500 agents. All of this is robust. We're going to see it in a minute. But what you can see here is some representative simulations. So each line corresponds to one simulation run. And what we're looking at is the percentage of cooperative outcomes, okay? The cooperation rate, if you like. How many pairs there are where both players have cooperated. And what we observe is that there's some variation, obviously, because there's mutation, there's errors, stochastic, but most simulations spend most of the time with a cooperation rate that is stable in time and is around a little bit less than 40%. And if you add the possibility to leave, so that would be in the repeated prisoner's dilemma, when you consider only the strategies that cannot leave. And when you consider all the strategies, you give the players the option to leave, what you observe is, again, a dynamical regime that is fairly stable, that most simulations will end up here, and with a much greater proportion of with a much greater proportion of pairs that are cooperating, with a higher cooperation rate. Okay, that's what we observe, about more than 20% more. Is this robust? Yes. What we did was these graphs show, again, the cooperation rate in blue for the voluntarily repeated prisoner's dilemma, where the agents have the option to leave, and in red for the repeated prisoner's dilemma. And the dashed line marks the baseline scenario. Okay, and what we did was, for instance, here at the top left, we study how the cooperation rate of this stable regime changes as we change the payoff benefit given by the cooperator, the parameter B. Okay, and we see that within a wide range, we observe that the option to leave does increase the cooperation. We do the same for the expected number of interactions, or for the continuation probability, and we observe this curious pattern that we're gonna discuss in a minute, okay? But basically what we're seeing is that when you have the option to leave, longer interactions, greater probability of continuation leads to greater cooperation. But if you don't have the option to leave, greater expected number of interactions lead to less cooperation. Okay, we'll see why in a minute. And for error rates, we see that when there are no errors, there's pretty much no difference between having the option to leave and not having it. But when errors are sizable, the difference is about 20%. Okay, and the same occurs with the mutation rate, with the probability of revision that hardly has any influence, or with the number of players. Okay, so what we're gonna see is pretty robust. What is this? So what we're looking at is the cooperation rate as a function of the expected number of interactions of stable couples. So basically the probability of continuation at another scale. And what we see that when players spend longer together, or have their partnerships do not break exogenously, the longer these partnerships last, with the option to leave, the longer the greater the cooperation rate. But without the option to leave, in the repeated prisoner's dilemma, we see a decline in the cooperation rate with the probability of continuation, which may seem counterintuitive, but remember there are errors. There is a significant amount of error, 5%, and partnerships like Tit-for-Tat, for instance, they may get into long chains of miscoordinations and defections, and the longer these chains are, the less the cooperation rate, and that is so. The error rate, a significant amount of error rate, is behind this pattern. Okay, so what we're gonna see now is what are the successful traits in the repeated prisoner's dilemma. So we've seen that there is a dynamical regime, and this dynamical regime is supported by strategies, by 3 or 4 strategies mainly, that have the following traits. So what we're looking at here in the table is for each possible history, so for each possible last outcome of the interaction, what proportion of agents are choosing C and what proportion of agents are choosing D. So what we see is that when most strategies, 87% of the strategies, cooperate with a new partner. Okay, so there are nice strategies. Those are the ones that are supporting cooperation in the repeated prisoner's dilemma. Once they start cooperating, they maintain cooperation by cooperating after mutual cooperation. So that is what 91% of the strategies in this dynamical regime do. They defect after having been exploited, okay? 91% of them do, and they keep on defecting if they can exploit their partner. Any questions or no? Okay. So these are pretty much I think the traits you could expect, while there's no clear pattern on what they do after mutual defection. So the most prevalent strategies in the repeated prisoner's dilemma are green. I mean, they share all the traits that we've just seen, these 3, green, win, stay, lose, shift, and Tit-for-Tat. And what we see, the usual run, and most of them are like this, is that these 3 strategies support this regime, and these 3 strategies, they have the traits that, or the first 2 have the traits that we've seen. And even though there's significant variation on which of the 3 or 4 is more popular at a given time, on average, if you take, if you look at the long run, the set of these 4 strategies that share the traits we saw before is very high and very stable. Now we're going to look at what happens when you give agents the option to leave, and it's completely different. When you give players the option to leave, what we observe is that the strategies, players do not cooperate on the first period. They do not start cooperating, and this is reasonably easy to understand, because if they started cooperating, they would risk being invaded by a defect and leave strategy. So a system with full cooperation is easily invadable because with the option to leave, there is this strategy that can defect and then leave and look for another random partner. So pretty much the most clear trait that we observe is players are not nice, if you like. They do not start cooperating. They do cooperate after mutual defection, because if in the first period they're not going to cooperate, they're going to defect. In order to get some chain of cooperation going, you need to cooperate after mutual defection. And in order to get that mutual cooperation going, you also need to cooperate after mutual cooperation. So these 3 traits are very clear. And the other trait, which is what distinguishes this system from the normal repeated prisoner's dilemma, is that most of them, 82%, leave after having been exploited. So instead of, for instance, defecting after having been exploited, they prefer to leave. And there's only 3 strategies that share all these traits. We call them leavers, okay? And they only differ in what they do after having exploited their partner, which is not very relevant because it doesn't happen often in these systems. And what we see is that, again, there's significant variation in this a representative run. So what we see is that the 3 levers together tend to be in very high proportions. So this would be the 4th box plot here. So the 3 levers together as a set, they're always represented in about 70% of the population. They represent 70% of the population. And which one of them varies in time and across simulations. But the 3 traits that we saw pretty much start defecting, cooperate after mutual defection and after mutual cooperation, and crucially, leave defectors are traits that are observed most of the time in this dynamic regime. While the set of strategies that do not leave, the set of strategies that were successful in the repeated prisoner's dilemma without the option to leave, pretty much vanish. They vanish completely. Okay, so now it's probably clear why the expected number of interactions of stable couples leads to greater cooperation when players can leave, but to less cooperation when players cannot leave, is because of what we said before, right? That if you're gonna be for long with your partner and there's the possibility of mistakes, then the longer, at some point there will be a mistake, and that will lead to some miscoordination, CDs or DCs, or even to some long chain of DDs. And the longer you're gonna stay with that partner, the longer both of you are gonna suffer this chain of miscoordination and mutual defection. While if you have the option to leave, when a miscoordination occurs or when you have been exploited, you can always leave and save yourself all these long chains of mutual defection. So that is why we see this pattern. Okay, those are
Can I
the...
ask a question?
Yeah, sure, thanks. Yes.
So are you saying, so the difference going to the right is caused by effects on the payoffs for basically what's the same distribution, or is there also a selective effect? So is the average frequency of the different strategies the same between, let's say, 20 and 100?
My guess is that it will be very similar, but I haven't looked at it. So the traits that we've looked at are for the baseline scenario, okay? For expected number of interactions equal to 20, this touch line. What you're asking, if I understood correctly, is whether that distribution of strategies is the same for 20 and for 100.
Yeah, so what you explain makes total sense, right? Even if you keep the distribution fixed, you would see the increase in the blue, yes, and the decrease in the red. But it might be that on top of that, there's also a selective change.
Exactly. I mean, if at the question time, we've got all these simulations, so I can send you the link where we can see it. We can see which strategies. I think they will be very similar, but you're right. There's 2 different effects. If you kept the distribution, I think, as you said, I think you're right. My impression is that you're right. That if you kept the distribution, you would observe this same trend. But it could be the case that the distribution is changing and then that could add or maybe subtract to this effect. Yeah, but there's two effects, as you said. Yeah. If we have time at the questions, we can look super quickly at it. Okay. Thanks a lot. Okay, so we did obviously some mathematical analysis to confirm all these simulation results. Many of you know here pretty much anyone who has worked in the option to leave lately know how that the expected payoff function, deriving the expected payoff function is not trivial. Here we've got mutation and, well, not mutation, sorry, errors, which makes it a little bit more complicated. But even if without the errors, the expected payoff function with the option to leave is not linear. It doesn't even admit a closed form algebraic expression when there's more than 3 strategies. So it's already quite a challenge. And using this expected function, we saw also important differences between the repeated prisoner's dilemma and the voluntarily repeated prisoner's dilemma. In the repeated prisoner's dilemma, there are several monomorphic strict Nash, but this is not the case in the when you have the option to leave. And actually, what we prove in this paper is that no memory 1 strategy is evolutionarily stable in the voluntarily repeated prisoner's dilemma for moderate error rates and for moderate continuation probability. But what we did is to study the mean dynamic of this system. So we study, well, as you all know probably, this is a system of the ordinary differential equations to which simulations with very large populations convert in a way. The difference between the solution trajectory of the mean dynamic and the simulations tends to 0 as the population size grows. And in our experience, and in this model in particular, even with population sizes of, say, 500, even 200, the mean dynamic is a good approximation. And it allows for a more in-depth analysis. And doing that, what we did is to study the mean dynamic of a reduced system with the most emblematic and successful strategies in the repeated prisoner's dilemma, all the Tit-for-Tat, Winstead, loose shift, and green. And we added lever 1 of these lever strategies that leave after having been exploited. The vertical line is the baseline scenario. We ran several, we solved numerically the mean dynamic from different initial conditions, and they all led to a unique global attractor, which is the one we're plotting here. We have no proof that there is a unique global attractor, but everything seems to indicate that there is. And as you can see, as the mutation rate goes to 0, the lever becomes dominant. So how does this happen? Well, it happens for a reason that has been explained already a few times in the literature, recently by Grasser and Matthijs and Takako and Julian. The reason is that the option to leave generates positive assortment, okay? And we're gonna see this. So what we're gonna see is to compare lever 1 that basically leaves after having been exploited with the equivalent strategy that does not leave but punish defectors by defecting, by staying and defecting. So we're comparing leaving versus punishing by defecting, and by studying lever 1 versus nasty Winstead loose shift, which is its counterpart that does not leave. And these two strategies, when they form part of the same population, they behave identically. Okay, so they're equivalent in any population composed by only them two. But when you match them with all D, they behave very differently. Okay, something that is interesting is that one nasty win win-stay-lose shift in a population of all D behaves exactly the same or has the same payoff, let's say, as one lever. And the same occurs with one all D in a population of nasty win-stay-lose shifters and one all D in a population of lever one. So the extremes of these graphs are showing the expected payoff of these strategies. If you compare the population of nasty win-stay-lose shift all D and the population of lever one versus all D, the extremes, the payoffs at the monomorphic populations are identical. But what happens in between is very different. What happens in between is as follows. The strategy that does not leave, in this case, when you confront it with all D, all partnerships will last the same on average because no one leaves. So all partnerships are gonna last the expected number of interactions of stable couples. And therefore, payoffs are linear, and this is what you observe. And in a system with some noise and, with some errors and mutation, what we observe is that there is a unique global attractor composed mainly by all D. But levers, when they meet an all D, the first time they both defect, but after having played the second time, the lever one at the second time step will cooperate, all D will defect, and then lever one will leave. And by leaving, it has an opportunity now to go to the pool of singles and try to meet another lever. When two levers meet, then that partnership is stable and will last as long as there's no exogenous breakup. So the couples made up by levers are very stable. They will last for very long, while any other couple made by all these and levers or just all these will break after, well, all these and levers will break after 2 periods, and all these will stay for long defecting. And because of that, because of this different rate of going to the pool of singles and different length of partnerships, the payoff functions are nonlinear. And for an equivalent population, which is what we're looking at here in the solid line, for an equivalent population, the strategy that punishes by defecting in partnership punishment will decrease, while a lever who disciplines all this by leaving and then has the opportunity to meet another lever will increase. And that's the main difference there. And another thing, and I'm about to finish that, another thing we found really interesting is what we pointed out at the beginning. What we saw is that in this system, like in some other evolutionary system, the behavior, the dynamics without error rates or with vanishingly small error rates are completely different from the dynamics we've been considering here, which have a substantial amount of error rates. When you look at these graphs, it may seem weird. Even, I mean, when we first saw it, we thought maybe we've got a bug or something. But I mean, at the end of the day, we have seen, or it's not difficult to create system, or in this case, to study reduced systems where you can make intuitive sense of why this happens. So here, what we see is a system with just 3 strategies: lever 1, Grimm, and Tit-for-Tat, and with a small error rate that we see here, 1 times 10 to the minus 3 or lower, because pretty much even for error rate 0, the simplex, the dynamics are very similar. We see a unique global attractor where lever 1 is hardly present, okay? Then if we increase just slightly the error rate, we see the appearance of another global attractor and another unstable point. And then if we increase just slightly more the error rate, but we're now at 5 times 10 to the minus 3, which is not much, we see a completely different global attractor from the one we saw at the beginning. And in this case, lever 1 is much more present. So to conclude, so what have we learned with all this? First, that environments or settings with significant error rates and persistent experimentation have often different dynamics, okay? And very often what we observe is just a small subset of strategies or a small subset of dynamical regimes that are observed in those systems. Then the option to leave, as we've seen, creates positive assortment. We already knew that in the literature. And for sufficiently large continuation of probability of continuation, cooperation is much greater, more than 20% more, and more robust with the option to leave than without it. This doesn't happen for low probability of continuation, but for reasonably moderate, yes. And cooperation in these systems, in the voluntarily repeated prisoner's dilemma, is sustained by strategies who leave. Strategies who do not leave basically vanish from the population. And as a final conclusion, what we see is that if you give agents the freedom to leave defectors, basically, this can lead to an improved outcomes at the population level, and especially as we've seen here in realistic settings where there is a lot of errors and experimentation. So that's everything I wanted to say. If you have questions, I'll be delighted to answer them.
Okay, thank you very much, Luis. And I shall stop the recording.
Okay, thank you.